Hey, just wanted to go over the Chapter 16 quiz for the few of you that took it, and for those of you that didn't, in case you just kind of wanted to see what it looks like, just to kind of wrap up Chapter 16 for you. So I'm going to run through it fairly quickly. I don't even have my calculator on me, so I'll probably set up the math, but I'm not sure I'll bother to solve it. First question on the individual part just starts off with all the strong acids and bases. I'm not sure I should bother to go through those, so just remember that there's 7 acids and 8 bases. So 7 of these and 8 of those. Good enough. The conjugate base of H2PO4 minus means that H2PO4 minus is acting like an acid. If it acts like an acid, it donates H. And so we're going to lose one of the H's and end up with HPO4 2 minus because we're losing an H plus. So essentially subtract H plus from this. That means we're going to do the reverse for the conjugate acid of HCO3 minus. That means it's acting like a base, so we're going to add an H plus to it. So add H, so the conjugate acid has an extra H, so it's H2CO3. Which acid is stronger, H3PO3 or H3ASO3? If you look on the periodic table, P is right above AS. As you go up on the periodic table, electronegativity increases. That is something we certainly need to know. And so H3PO3 would be the stronger acid because the P adds more to the polarity of the molecule and therefore allows H to be more readily pronated than AS does. So H3PO3 would be stronger. For each of these salts, we're talking about whether they're acidic, basic, or neutral. You just have to figure out, are each of these ions going to do something? So does Cu2 plus do something? Does Cl minus do something? Cl minus doesn't do anything because it doesn't stick to H plus, so it doesn't do anything. Cu2 plus, though, does stick to OH minus. And because it sticks to OH minus, there's less OH minus. So OH minus goes down. That makes something acidic. The situation with SR2 plus, CN minus, SR2 plus is part of a strong base. It does not stick to OH minus, but CN minus certainly does stick to H plus, so H plus goes down. That means it's basic because there's less acid in there. And KClO2, K plus, as we know, never does anything. ClO2 minus is not one of the parts of the strong acids, and so it does stick to H plus, and so it also is basic. We got into a little bit of the math situation here because strontium hydroxide is a strong base. To find the pH of it is simply a matter of doing 14 plus the log. The one trick question here, though, is it's not 0.250. It's 0.250 SrOH2 times 2 OHs for every 1 SrOH2. So that would be the 14 plus the log of 0.5. Okay. Again, no calculator on my person at this point, so don't worry about the answer. If a solution of HCl3 has a pH of 2.44, the molarity of OH minus, well, H plus is simply 10 to the negative 2.44, and then OH minus is 1 times 10 to the negative 14th over that number. Or you could certainly do that 14 minus 2.44 equals POH and do 10 to the negative POH. Either way, we'll get you the same answer there. Last part, last part of the individual part, 0.25 molar HNO2. If it's Ka, is that value. So that's just a weak acid all by itself. So just 4 times 10 to the negative 4th equals x squared over 0.25 minus x. Solve for x. X represents H plus, and then do the negative log of x. Then we got to the partner part. I'm just supposed to write the Ka expression for this. It looks like they all do. Ka simply being the molarity of H3O plus times A minus all over HA. And the initial molarity of 0.040, we got a 7.2% ionization level. So Ka would equal 0.072, that's the percentage, times the initial molarity. That would be X. And then since it's x squared, that would be over. And then there's a couple of different ways to do this. One of the ways to do 92.8% times 0.040, how much of the original molarity is still there. That's sort of like doing a multiplication version of molarity minus x. And then in this 0.5 molar NaA, again, I don't care about the Na, that's the solution of A minus, that's the conjugate base. So what you'd have to do is say that Kb for that base is Kw over the Ka that you just calculated in part B. And then that would simply be equal to x squared over 0.5 minus x. And 0.5 is the initial molarity. X in this case, because it's a base, represents both HA and OH minus. And then you could find A minus, because that would be your sort of final molarity here. So this would be A minus. And then the last two parts here, 0.1 molar HA and 0.35 molar NaA. If we go back to the Ka expression that we wrote earlier in the problem, Ka being H3O plus times A minus all over HA. We've got a bunch of those values here. We solved for Ka already, so we know Ka. Solve for that earlier in the problem. We don't know H3O plus. That's what we're going to solve for because they're asking us for pH. We do know A minus, it's 0.35. Technically it's 0.35 plus x, but who cares about the plus x? And then that's over 0.10 minus x, but again, who cares about the minus x? So that would be pretty easy. And then similar in the second part here, Ka, we still know that. In this case, though, we know what the H plus is going to be because it's going to be 0.05. Technically, it's going to go up ever so slightly. But we don't care about that because this makes 100% of H plus, so it's going to be that value. We don't know what A minus is, so that's x. We're going to try to solve for that. And then we know that HA is 0.25. And technically, it's going to go down by x, but again, who cares about that? So there's the chapter 16 quiz without the multiple choice. It's just too much of a pain to try to fit that onto about 8 different pages here, but I can certainly go over that at some point. Again, this is a non-essential topic these days for the AP, so I'm not too worried about it, but in case you just want to kind of consolidate your knowledge and make sure you remember things from chapter 16, take a couple minutes and watch this and let me know if you have any questions.